Okay, well, it's 5 o'clock here in London, so we've got a lot to cover today, so let's get off to a prompt start. So good morning to those of you on the West Coast, good afternoon to those of you joining from the East Coast, and good evening to anyone joining us from Europe or stations further east. Thank you for joining this, the 23rd of our regular series of seminars on pumping topics. Well, today we had 232 registrations for the morning session, and this afternoon session, it's 269, so that's very gratifying. This session will last about 45 minutes, allowing us still time for a Q&A session after the presentation. So let me restart the share. There we go. So here, as usual, is a listing of all the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials from our website. Use the following link, shortcourses.ruhrpumpen.com. Or you can go to ruhrpumpen.com and follow the link to RP short courses. If you go to ruhrpumpen.com, you get to this screen, and here is the link to the RP short courses. If you click on that, it takes you to this screen, which you can also access directly using that link, shortcourses.ruhrpumpen.com. You'll see all the courses listed, and you can click on any of them to see the course material. All of the previous 22 courses are up there. Well, here is what we'll be covering today, pumps for the desalination market. Now, as usual, we'll be holding a Q&A session at the end, so please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I will address those that I can live at the end of the session, and the rest will address by email in the coming days. We are recording this session and will make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow. Now that PDF version will be complete with presenter notes, essentially the script of this presentation. You'll also receive the Q&A summary from both of today's sessions. So here's the agenda for today. We'll have a brief generic overview of the desalination process. We'll look at the various pumps required at various stages of the process. And we'll look in a little more detail at some of the key pumps that are used. And then finally, we'll look at the quality inspection and testing. A brief and very much generic overview of the desalination process. It has to be thus, as there are just so many variations depending on throughput, quality of water, regional preferences, who the design engineering contractor is, and on and on. We'll take some time going through the various stages. Pre-treatment here on the left, 4 stages of that. Main treatment here in the center, 3 variations on that, and post-treatment here on the right. And as you'll see at the top, Ruhrpumpen has pumps for every stage and duty on the plant. We're the full line supplier. So let's start on the left, and we start with the intake pumps. Pump number 1, intake pumps. Most commonly, these are large vertical pumps, type VS1, if we're talking seawater. But horizontal pumps, BB1, they're quite common in Africa. And on small plants, they sometimes use self-priming pumps. This is the first pre-treatment. It's not always used, coagulation. DAF stands for dissolved air flotation. Chemical additives and flocculants are added and air bubbles float the impurities to the surface. Pump 2 here, DAF pumps. This is an OH1 pump, typically 300 to 500 cubic meters an hour at about 7 bar. Now, you're going to hear quite a lot of numbers, flows and heads in the next 20 minutes or so. They are purely indicative, just typical. You needn't write them down or try to remember them. You will get a PDF copy of this slideshow, complete with my speaker notes, and that will include these figures. Let's talk about metallurgy for a moment. The main pumps, these here, are in seawater service, and they're usually manufactured in super duplex. The auxiliary pumps down here are not in seawater service. They're in freshwater or chemical service. Now they're usually duplex. They could be 316L, but duplex is about the same price, and we tend to stock that in this material these days. So the second pre-treatment is filtration. Two common types, gravity and pressurized filtration. Gravity filtration needs no feed pump. The main intake pumps do the job. But pressurized filtration needs a filter feed pump, pump number 4, filter feed pump. And this will be an OH1 pump, 6,000 cubic meters an hour on a large plant, 500 cubic meters an hour on a small plant at about 5 bar pressure. Pump number 3 here, the backwash filter pumps. This will be a large axial flow OH1 pump, 800 to 6,000 cubic meters an hour maybe, at say 25 meters head. Some plants use ultrafiltration or microfiltration. Pump number 4 for this service, filter feed pump, 500 to 6,000 cubic meters an hour at about 6 bar max. Pump 5, the backwash pumps, again, same as pump 3 above. So 800 to 6,000 cubic meters an hour maybe at, say, 25 meters of head. Auxiliary pump 1, the flushing pump, a small OH1, say 600 to 700 cubic meters an hour. That would be on a 4,000 cubic meter an hour plant, so that's an average size. Auxiliary pump 2, CIP pumps, that's clean in place pumps, chemical cleaning. That'll be a small OH1. And the fourth of the pre-treatments, neutralization. This is a critical process to protect the membranes. Auxiliary pump number 3 here, the neutralization pumps, small OH1 pumps in duplex, pumping acids and alkalis. Moving on now to the main treatment. What we're doing is to raise the pressure at the inlet to the reverse osmosis membranes to a value significantly above the osmotic pressure of the raw water. Now this value, the osmotic pressure of the raw water, this value varies widely geographically according to how salty is the water. A typical figure might be 40 bar, in which case we would want to operate at 70 bar to maximize throughput and get a recovery rate of 40 to 45% of the inlet flow. We show here 3 different systems. 2, 3. The difference being the method of the energy recovery. You have 70 bar going in, and the permeate, the clean water coming out, is at 0 bar, and the brine coming out of the brine coming out is at 67, 68 bar. So you definitely want to recover that sort of energy. The first method uses a turbocharger, which is a Francis or Pelton wheel on the same shaft as pump impeller, like this. Now, there's the Pelton wheel this end and an impeller, pump impeller on this end. This can be difficult to control. The turbine can act as a brake on the pump and reduce the throughput. So it's not so popular these days. System C here uses a self-standing Pelton wheel for energy recovery, like this. This is connected to a double-ended motor shaft, and so it doesn't affect the flow and head like the turbocharger did in System A. Again, it's not so common these days. This, treatment B, with a pressure exchanger energy recovery. This is the most important system. Incoming seawater gets split into 2 streams and goes to the high pressure pump and also to the pressure exchanger, the PX. Now this PX needs a minimum of 1 to 2 bar inlet pressure. So depending on the seawater pressure, you may need a booster pump in here, which is pump number 7. An OH1 giving 2 to 3 bar, say. The high pressure brine gives up its energy in the pressure exchanger. And the pressure here may be about 66 bar. So we need a special pump here, pump number 9, to boost the pressure from 66 bar back up to 70 bar, the same as the outlet from the high pressure pump. I say it's a special design of pump. It's an OH1 pump and it's designed for 69 bar inlet pressure and the high thrust that results from that. Pump number 6 is an NPSH booster for the high pressure pumps. Now either or both of these pumps might very well be under variable frequency drive control to compensate for seasonal variations, winter, summer, rainy season, dry season. And these variations can be considerable, maybe 6 bar, maybe 70 bar variations. In general, it's more efficient to have the low voltage booster pump, so pump number 6, under VFD control, than it is to have the high voltage, high pressure pump. High voltage VFDs are very expensive. Pump 6 typically is an OH1, generating about 180 to 190 meters of head, but down to about 40 meters with variable speed control. Occasionally, it'll be a BB1 pump. The high pressure pumps, 8.1, 8.2, 8.3, there'll be a BB4 or BB3, depending on the spec and customer preference. Auxiliary pumps 4 and 5 will be OH1 pump in duplex. Auxiliary 4 and 5, that's the reverse osmosis flushing pumps and the clean in place pumps. As I said, the permeate comes out at about 0 to 1.5 bar, and the brine comes out at 68 to 69 bar. Let's look at the pressure exchanger. I won't try to explain here how it works. I'll just refer you to the Energy Recovery Inc.'s website here, where they have a very good video showing how it works. Post-treatment. Well, in all three main treatment variants, we see the option for a second pass reverse osmosis membrane bank. This may be required to meet the local water quality requirements. Now, the feed water to these is permeate water from the first stage, so its osmotic pressure is far less, and so the working pressure will be far less too. Feed pumps, P10, second pass pumps, will have an inlet pressure of around 0.5 bar and an outlet pressure of about 12 to 15 bar, compared with 70 bar, you'll recall, on the previous one. It's relatively clean water, so duplex stainless steel can be used for this feed pump, or these feed pumps. Auxiliary pumps 6 and 7 will be duplex material OH1 pumps. And so to the final stage of post-treatment to meet the required water quality. There'll be pH adjustment with lime and dilute acid and chlorination. Auxiliary pumps 8, 9 and 10, lime dosing, CO2 dilution and neutralization pumps. They're duplex OH1 pumps, 200 to 300 cubic meters an hour at 20 to 30 meters of head. And finally, the product water pumps, pump 11. This will be a duplex material, very high flow, low head pump, maybe an OH1 or more likely a BB1 axially split case pump. Here on the left is what we've just looked at, a dedicated train. One pump feeds one membrane bundle. Here on the right is the common manifold configuration, in which one high pressure pump feeds 2, 3 or even 4 racks. So flow rates of 3,000 to 4,000 cubic meters an hour instead of 1,200 cubic meters per hour. The high pressure pumps will be a 1 or 2 stage BB1, and the booster pumps will be an OH1. In the second part of this presentation, we'll look in a little more detail at some of the key pump types used in the process. Firstly, the OH1 pumps. These are built to ISO or ANSI international standards, and these are dimensional standards leading to high levels of interchangeability. Up to 8,200 cubic meters an hour and heads to 180 meters. The next few slides are going to look at ANSI pump features. Here's a typical ANSI or ISO pump. It's foot mounted, has a formed steel base plate, sometimes with a drain pan, and it has a foot mounted motor. A common variation is the C-frame adapter, which will allow you to use a NEMA C-flange motor instead of a foot-mounted motor. Here are some of the features of an ANSI or ISO pump. Now, this is, of course, the Ruhrpumpen offering, but other major manufacturers are very similar, by the very nature of the ANSI or ISO specification. Bare shaft pumps are designed to be interchangeable between manufacturers. Bearing life, according to spec, is 17,500 hours, but Ruhrpumpen have upgraded to 50,000 hours. I'm not sure whether others have done likewise. ANSI B73.1 specifies sizes up to 4,000 gallons a minute, but Ruhrpumpen goes up to 36,000 gallons a minute in desalination service. We've added a lot of sizes. In fact, we've got about 70 pump sizes. They go up to 36,000 gallons a minute and heads to about 650 meters. 650 feet, I do beg your pardon, 200 meters. We have 4 options on bearing lubrication. Many manufacturers, including Ruhrpumpen, use semi-enclosed impellers, and these can be adjusted in service to allow for wear. And here is how the axial clearance is adjusted. This bearing carrier here is threaded to the pump frame and rotates to displace axially the entire rotor. So the entire rotor will move forward or back and open or close this clearance between the impeller vanes and the pump casing. Here you see it a little better, 3 hexagonal bolts. You release those and then you can twist it round, click, 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 each click being 0.08 millimeters or 3 thou. But an optional build is the fully enclosed impeller with replaceable wear rings. We have 3 interchangeable stuffing boxes, one for packing and cartridge seals, one for dual seals, that's the big bore, and one for solids handling, that's the tapered bore. So in desal plant operation, usually it will be this one for standard cartridge seals. Now, I mentioned earlier some special design pumps of OH1 type, designed to handle 66 bar of suction pressure. That was pump number 9. Here are those pumps, and we're actually designing them for 90 bar max allowable working pressure. We've had to beef up the pump to withstand this pressure, but also to accommodate the thrust. As you will realize, 82 bar pressing in this direction is going to try and push the rotor out the back end of the pump. So we've designed more robust thrust bearings to accommodate this. BB1 pumps for the higher flows and heads, 30,000 cubic meters an hour, 340 meters. These are an axially split case pump, so you can remove the top half casing and then remove the rotor for servicing. They have a double suction impeller and a double volute casing to give low shaft deflections, which leads to long seal life and 100,000 hour bearing life. Case wearings are standard and impeller wearings are optional. Vertical arrangement is available to simplify piping and minimize the floor space. A vertical mounted pump will take up about 20% of the floor area of a horizontal base plate mounted pump. The high pressure reverse osmosis feed pumps Well, for small pumps, we have this baby pump, the GPA, up to 300 cubic meters an hour, 720 meters. Its big brother for larger pumps, larger plants, is the GP, and goes up to 1,000 cubic meters an hour. Now, if you attended session 21 of these courses on BB4 pumps for the power market back in March, about 4 weeks ago, then the next few slides will be familiar to you. BB4 pumps described by API 610 as single case, multi-stage, radially split case pumps, but also popularly known as ring section pumps, segmental ring pumps, and tie rod pumps. Here's a photo from a recent order. You can clearly see why they are called ring section and tie bolt design. This is the Ruhrpumpen model GP pump for desalination service. It's based on our market-leading BB5 barrel pump hydraulics. It's a ring section pump with tie bolt design, and it's centerline mounted. The hydraulic design is designed for 2-pole, 50 hertz or 60 hertz. It's not a high-speed pump. It doesn't need to be either. High and low flow impellers are available for each pump size. This is good for retrofits and re-rates for duty changes in the future. A low NPSH first stage is available, and we have designs for interstage takeoffs. This is a requirement in the power industry. It's not really necessary in the desalination market. The hydraulics have been and continue to be optimized by CFD, computational fluid dynamics, to maximize efficiency. And this is an ongoing, continuous improvement. Here's the range chart at 50 hertz, flows up to 1,200 cubic meters an hour and heads to 2,000 meters. And at 60 hertz, flows to, I'll give it to you in gallons this time, 5,280 gallons a minute and heads to 10,000 feet, not 1,000 feet as we show here on this scale. We have 3 mechanical design standards. Each can be upgraded to the next level. You can pick and choose features that you want without necessarily going the full API route. Desalination plants seldom require full API compliance. So this is what it looks like in section. You can see the inline stacked impellers, all facing in the same direction. The diffusers, or ring section construction. The tie bolts, holding them all together. The balance line here between the seal chambers. And here the thrust balancing device. We're showing here a balanced disc. The balanced drum is an option. We'll come to that. It's centerline mount, and these flange ratings can be 600 pound, 900 pound, 1,500 pound, or 2,500 pound. So that's around 2,500 PSI in super duplex. You have confined O-rings at each stage, and these can be in various materials according to the service. Can be NBR, which is acrylonitrile butadiene rubber, or EPM, which is ethylene propylene rubber. That's probably the most common, but There are several other designs right up to perfluoro rubber, for example, and tetrafluoroethylene propylene. So some expensive options when you need them, but not for desalination work, I think. Here we have the optimized inlet channel to ensure good flow into the impeller. You saw this in the earlier slide on suction chamber CFD design here. So it's been optimized to ensure peak efficiency. We have investment casting impellers to optimize the efficiency and repeatability. The impellers and the shaft are balanced to ISO 1940 grade 2.5. We have high and low flow hydraulic versions of each pump size available. And this is important for retrofits and re-rates. Impeller mounting and shaft, we have two designs. One with a straight shaft and sleeves securing each impeller. This is used on the smaller, lower pressure pumps. The second version, the API version, with a stepped shaft and impellers individually secured by split rings. This is used on larger, higher pressure pumps. Wearings. Well, the base design case has case wearings only, no impeller wearings. Impeller wearings can be fitted later at the first service. After 3 to 5 years, when some wear has occurred, you can remove the rotor, remove the impellers, machine away and put impeller wearings on at that stage. There's no advantage to fitting impeller wearings at the outset because you still have to machine them off after 3 to 5 years to fit new ones on. So our recommendation is case wearings only initially. We run with closer clearances than API recommends, and this is for optimum efficiency. We're pumping clean water with no solids, so it's not high temperature, so it's fine to use closer wearings, clearances, and get the higher efficiency. We can fit peak wearings, and then the clearances can be closer still, and the efficiency improved some more. These are shown in black here. Or you can have replaceable wearings for both case and impeller from the outset. This would be an API 610 option. In this case, blue are the case rings and gold here are the impeller rings. Or possibly a combination of the two. Here we go with peak case wearings in black. We run with closer tolerances, clearances rather, and we have metallic impeller wearings shown here in gold. Here is the bearing housing, which has vertical fins to provide optimal cooling. You can see here the radial bearing, which is a single row cylindrical roller anti-friction bearing, ring oil lubricated, and an Impro bearing isolator. If you choose or need the option of tilting pad, hydrodynamic bearings, you'll need a force feed lube system, in which case we have this shaft-driven main oil pump, which bolts on the end here. Which brings us to hydraulic balancing or thrust balancing. With a BB4 pump, you have stacked impellers, all facing the same way, so the thrust builds up and is more than a conventional ball bearing can take. So there are several ways of handling this thrust. You can have opposed impellers, 5 facing one way, 5 the other, thus equalizing the thrust. And this is what we do on BB3 and BB5 pumps. On BB4 pumps, we use either a balance disc or a balance drum. Here is the balance disc. You have full discharge pressure on this side and suction pressure acting on this side. The pressure, the thrust, is broken down by close axial clearance between these two faces here. It balances out 100% of the thrust, so no thrust bearing is required, just a radial bearing. It's a little clearer in this slide. Suction pressure on this side, discharge pressure on this side, and the pressure breakdown across this face. Now, the close running clearances mean it's only suitable for clean fluids, so it's ideal in desalination reverse osmosis plants. API 610 is written with process fluids in mind, which are frequently hot and they frequently contain solids, and so they say this design is not suitable for that. Well, that's right, it's not suitable for that. And API 610 therefore does not allow balance discs, but they are ideal for clean water service like this. Here is the balance disc, and here you see the balance line here, which ensures that you have suction pressure here on the suction side, but also here on the outboard end. Now, with these close running clearances, there's a risk of the faces touching and wearing prematurely, especially during startup and shutdown. So there is the option of a lift-off device comprising a preloaded spring and an angular contact bearing. This will ensure that the thrust disc faces are held open during startup and rundown. Now here is the alternative thrust balancing mechanism, the balance drum. It's required for API 610 pumps, and it's used on the larger sizes of BB4 pump. Thrust is broken down in the radial direction. It has greater clearances, and so it only breaks down 85 to 90% of the thrust, so you will need a thrust bearing as well. This should be clearer. You have suction pressure on this side, you have discharge pressure on this side, and the pressure breaks down across this clearance. Not as efficient as the disc, but better for solids handling. We have several bearing combinations according to your needs and preferences. Here is the simplest and least expensive, and it's used with the balance disc. We have no residual axial thrust to balance, only radial loads, basically the weight of the rotor. So we have a simple ring oil lubricated roller bearing. If you prefer, on larger sizes, a hydrodynamic bearing, a sleeve bearing, and it's still ring oil lubricated, no force feed lubrication required. With the balance drum, you have residual thrust to accommodate. It balances only 85 to 90% of the thrust, so you need an angular contact bearing, which can be ring oil lubricated to take that residual thrust. On larger pumps with higher residual thrust, or when specified by the contractor consultant, you can have a hydrodynamic or tilting pad Kingsbury type bearing, and this would require a force feed lube oil system. The nuts on the tie bolt system need to be tightened to the correct torque. Now on smaller pumps, a torque wrench will be suitable. On larger pumps, tightening the tie rod nuts can be an issue. You may need a hydraulic nut tensioner a very expensive, large, heavy item. But there is an alternative: multi-jack bolt tensioning, super bolts. This is the coolest thing I ever saw. Multi-jack bolt tensioning, widely called super bolts, although this is actually the trade name of Nordlock. Other manufacturers of MJT exist. It allows you to tighten these nuts using conventional hand tools instead of requiring a hydraulic bolt tensioning tool. You tighten the nut by tightening each of the jack bolts in turn using conventional hand tools. Or you can buy a super bolt tool to make it even easier. Tightens all 6 jack bolts evenly at the same time. So that's the BB4 pump. The alternative to the BB4 is the BB3, axially split case multi-stage pump. Axially split, so you can remove the pump rotor for maintenance or overhaul while leaving the pump case in place in the pipework. 2 models in the RP range: the JTN for lower flows and heads, the SM for higher flows and heads. So here we see the pump casing, number 1, which is a center line mounted. And as I said, it's axially split case. You can remove the rotor and take it back to the workshop to service it, leaving the casing in place. Here are the bearing housings, number 2. There's the mechanical seal chamber, number 3. And number 4, these are the impellers. The impellers are in a back-to-back arrangement, half facing one way, half the other. This means that the hydraulic thrust is balanced out, and you don't need expensive tilting pad bearings and lube oil systems. The flow path is like this. You can't see it, but the suction flange is on this side. So it comes in here to the suction, into the first stage, out into the second stage, out into the third, fourth, fifth, and then it gets into this crossover and comes back in the other direction. Stage 6, out, 7, 8, 9, 10 in this 10-stage pump, and the flow comes out of there, out of the discharge. Now the JTN is a diffuser design, and the SM is a volute design. So why the difference? Why do we have 2 designs? Well, we use diffusers on the smaller sizes, the JTNs, as they are machined from solid and give excellent repeatability, even at small sizes with small flow passages. Small volutes are difficult to machine and polish, so they're not so good on the smaller size pumps, which is why we use the diffusers. They give better performance and efficiency. But on larger pumps, the flow passages are larger, and you can easily get in there to machine and polish for optimum efficiency. So volute designs are the better solution at larger size pumps. Impellers and cases are fitted with wear rings, number 6. And finally, the vent and drain. Moving on, a BB1 pump, our type ZM, is sometimes used as the high pressure feed pumps, and it's frequently used as the product water pumps, sending the treated water into the water main. They're a high pressure BB1 pump, up to 9,000 cubic meters an hour, 650 meters. Here we see it as a single stage pump. and here as a two-stage pump. In this case, both stages are double suction. Well, here the first stage is double suction and the second is single suction. On small RO plants at low flows and high pressures, a positive displacement pump might be the better option. So triplex and quintuplex plunger pumps. While they are more expensive, they have a very high efficiency, up in the 90%. And they're particularly useful for ZLD, zero liquid discharge process, which is a low flow and very high heads, greater than 100 bar. The main intake pumps are most frequently vertical turbine pumps. Flows up to 90,000 cubic meters an hour, heads up to 70 meters. Now we show 70 meters here because that's all you normally need as an intake pump. But we have designs, of course, that go much higher than that. I did a session on these pumps in January last year. It was session number 11. So you might like to review that session. If you missed it, you can download it from our website. Self-priming pumps are sometimes used as intake pumps on smaller plants, and they're sometimes used for chemical dosing. The intake pumps on small RO plants are sometimes submersible wet pit pumps, like this. And finally, we'll move on to quality and inspection, but I'm not going to spend long on this. Ruhrpumpen is a high-quality manufacturer of pumps to many industries. The oil and gas industries require a lot of inspection and testing. Desalination plants typically do not. So the base starting point for these pumps is non-witness performance, non-witness hydro, non-witness dynamic balance, 2.1 or 2.2 material certs, and visual examination of components and the final assembly. But we can do pretty much whatever you want and whatever you want to pay for. As you see, we can witness the performance tests, we can carry out vibration tests, bearing temperature tests, noise level measurement, NPSH tests. All of these can be witnessed if necessary. Strip test, witness the hydro test, witness the balancing, dynamic balancing of the couplings, 3.1 type material certification, PMI, liquid penetrant examination, magnetic particle examination, ultrasonic testing, and radiographic examination. So all of these things can be done. Because we do it every day for the oil and gas industry, we can certainly do it for desalination plants. But generally, it's not required. The usual standard is really fairly basic non-witness tests, standard non-witness testing. Well, that pretty much concludes the fun for today. Here is where I get to advertise the next of the short courses, which is going to be on cryogenic pumps used in the liquid oxygen and liquid nitrogen business. And also I'll look at submerged electric motor cryogenic pumps for the LNG and LPG services. That's on Thursday, the 25th of May, which is in 4 weeks' time. After that, we may get one on magnetic drive pumps before the summer holidays start. I'm going to leave the meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. And those that need a fuller answer will be answered in a few days, either by me or by our product experts. Anything you think of later, send an email to info@shortcourses.ruhrpumpen.com. Our marketing team are standing by to direct your questions or suggestions to the best person to answer them. Now, they will also be sending you the YouTube recording and the PDF of the presentation. If you need a certificate of completion for this short course, again, info@shortcourses.ruhrpumpen.com. Now here, as usual, right at the end, 8 slides about Ruhrpumpen that remind you of who we are and what we do. Now, you've all seen these before, so I won't spend time on them. They'll be in the PDF copy of the presentation you get, so you can peruse them at your leisure. So now, on with the Q&A. Let's have a look and see if I have any questions. Yep, we have a few here. HF Yi has said, which one is more suitable for water pipeline, BB3 or BB4, and why? It is largely a matter of opinion and price. On the smaller sizes, the BB4 is going to be the better, cheaper option. The BB4 will usually be the cheaper option. BB3, big advantages that has is that it's an actually split case pump. You can remove the top half of the case, you can remove the rotor and take it away to the workshop to work on it. And you probably have a warehouse spare. You can bring that in, drop it back in, and you're up and running in one day. The BB4, you have to remove the whole pump to service it. BB3 also has the advantage of opposed impellers. I gave the example of 5 facing one way, 5 facing the other way. Balances out the thrust. There's no residual thrust, so you've got you don't need a tilting pad bearing or anything. Even at quite large sizes, you can get away with having angular contact bearings, which are ring oil lubricated. So largely that's the advantage. Probably when you get to the larger pumps, the common manifold pumps, higher flows, you're probably more moving into the BB3 away from BB4s. Dave Mellis said, is this presentation recorded and available for later viewing? Yes, it is. You will get a YouTube link to be able to see this, and you'll also get a PDF version of the slideshow with my commentary on it as speaker notes as well. An anonymous attendee has said, how is the ND non-drive end bearing lubricated for BB4 pumps? Excuse me a minute while I cough. The non-drive end bearing, now that would be ring oil lubricated normally. It would, you see, if you've got a balanced disc, it's a rolling element bearing and it's ring oil lubricated. If you've got a balanced drum, you've probably got a thrust bearing there, which is going to be an angular contact bearing, again, ring oil lubricated. Only at the larger sizes might you be needing a tilting pad bearing, and then you'd need an external thrust, external lubrication rather, an external lube system. And that's the point at which you might want to consider switching over to a BB3, which again with opposed impellers, balanced thrust. Even at quite large sizes, you still don't need a lube oil system because of that balanced thrust. Anonymous attendee again, probably withdrawing the question. Looks like bearings of both drive end and non-drive end are oil lubricated. Yes, that's correct. Yes, they are. Anonymous attendee says, where can be found the PowerPoint of this presentation? If you've registered with us, then you will receive it the link to a YouTube video, and you'll also get the a PDF version of this presentation. That at the moment appears to be all the questions. Just look in the chat and see if anyone's put something in the chat. No, not in the chat. In which case, if there are no more questions, and it's 5 to 6 here, which is very near to beer o'clock, in which case I will say thank you for attending. I enjoyed preparing it and presenting it. I hope you found it useful. And I look forward to seeing you again on the 25th of May for the next session on cryogenic pumps. Bye-bye.